So, I have a quick question before we get into the astrophysics for today's deep dive.
Yeah, sure, go ahead.
Did you ever play hide and seek with that one friend who was just, I don't know, way too good at it?
Oh, yeah, the one who hides in plain sight.
Exactly. You check the closet behind the curtains, nothing. And then they just jump out from a spot right in front of your face.
It's the worst. But, I mean, the stakes today are a little higher than a backyard game.
Just a little.
We're talking about a cosmic game of hide and seek where the hider is a massive star about to explode.
Right. And the seeker is humanity's most advanced eye in the sky. We have a really exciting stack of research on the desk today.
It's an incredible magic trick.
It really is. We are exploring the first published detection of a supernova progenitor star by JWST, a star that Hubble had looked at and missed completely.
Yeah, we're heading about 40 million light years away to the spiral galaxy NGC 1637.
And missed completely is the key phrase. Hubble looked at these exact coordinates in August 2024 and saw nothing.
Literally just a dark patch of space.
Which is wild when you consider what was actually there. It was a red supergiant,
A massive one.
roughly 100,000 times more luminous than our sun.
Right, so for Hubble to miss a light source that powerful, we have to be talking about immense optical depth.
The star was suffering from extreme extinction, right?
Precisely. It wasn't gone. It was shrouded in a thermal veil, this exceptionally dense shell of dust that it had created itself.
Wow.
And this dust absorbed almost all the visible light, making the star more than 100 times dimmer in the optical wavelengths that Hubble uses.
So the photons are just getting trapped and re-radiated as heat.
Yes.
And that is exactly where JWST changes the game, because it doesn't rely on visible light.
It doesn't. Researchers use JWST's specialized instruments and NIRCAM for near-infrared and MIRI for mid-infrared.
Like two different sets of thermal goggles.
Exactly. And NIRCAM peers through the thinner dust, while ERI detects the warm glow of the dust itself. When they combined these in 2024, they pierced right through that veil.
Saw the glowing red progenitor star clear as day.
But the composition of that dust veil is where the story gets really fascinating.
Because normally we expect circumstellar dust around red supergiants to be silicate-based.
Yeah.
Basically rock or sand.
Yeah. But the spectral analysis here showed something else entirely. It was carbon-rich.
A massive cloud of soot.
A giant soot blanket.
And that implies some serious internal turbulence. Because standard stellar evolution says heavy elements like carbon are synthesized in the core and stay deep inside due to gravity.
You've hit on the mechanism perfectly.
So it must be going through violent dredge-up phases.
It's convective mixing. As the star approaches its end, the internal layers become unstable. Giant convection currents like boiling water on a stellar scale dredge up that carbon.
And bring it to the surface.
Right. The star then ejects it via what we call carbon burps.
Carbon burps, I love that. And that creates the thick soot blanket that blinded Hubble.
Yes, and this mechanism actually provides the missing puzzle piece for a crisis that has bothered astronomers for years.
The missing red supergiants problem.
It was a genuine crisis. For decades, the numbers just didn't add up. We'd see massive stars, but rarely saw the high-mass ones actually explode.
Theories were all over the place.
Yeah.
People thought maybe they collapsed directly into black holes.
Or that our models of stellar evolution were fundamentally broken.
But they weren't vanishing and the models weren't breaking.
No.
The stars were just hiding behind their own exhaust.
Exactly. This discovery of supernova SN 2025 suggests that a massive population of these stars cloak themselves in dust right before death. We just didn't have the infrared sensitivity to see them until now.
It's a classic case of needing the right tool for the job. You can't find a heat signature with a visible light camera, which actually reminds me of what our friends at Embersilk are doing.
That is a great parallel.
Right. If you are trying to integrate AI into your business or personal life, there's just so much noise and dust out there. The hype, the confusing tools.
Endless options.
Exactly. Embersilk acts like that infrared filter. They specialize in AI training, automation, and finding exactly where agents can make the most impact for you.
They help you see through the noise.
To find the solution hiding in plain sight, you can check them out at embersilk.com.
It really is all about clarity. And bringing that back to our supernova, this clarity from JWST signals a completely new era.
We're moving from guessing to knowing. We aren't just waiting for things to explode anymore.
We're characterizing the unseeable. We are entering a golden age of stellar forensics.
It's incredibly optimistic.
It is. With JWST and the upcoming Nancy Grace Roman Space Telescope, we can catalog these doomed, dusty stars before the supernova event. We're refining our understanding of the universe in real time.
Validating that our technology is finally catching up to the cosmos.
Exactly.
It changes how you look at a dark sky. We used to think the darkness was empty, but now we know it's just full of giants waiting to be found.
And that leads to a really provocative thought to leave you with.
Oh, lay it on me.
If a star 100,000 times brighter than the sun can hide right in front of us behind a bit of carbon dust, what other massive cosmic structures are sitting right here, invisible, just waiting for us to invent the right lens to reveal them?
That is something to chew on. If you enjoyed this podcast, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.